Good afternoon, GIS 200. If you're watching this, then you're probably sitting at home enjoying the snow day, as our campus has been closed for all day Tuesday, and so class has obviously been canceled. However, as I mentioned at the beginning of the semester, when classes are canceled, we'll proceed as best we can so that we don't fall behind. So just want to cover a few things and give you a few updates on some stuff before I proceed with what you need to do. First off, take note that there is a new updated syllabus posted on the Blackboard site reflecting the changes in the schedule to accommodate today's bad weather. The materials and deadlines have been reorganized basically to facilitate this change in schedule. And so I'm going to have a video lecture of the material that we were supposed to cover this week, which was relatively short. We had some other things that we were going to cover, which I have moved into next week. And so that won't cause a problem. That'll still work out fine. But what you do need to do is complete the third online learning module as listed on the syllabus and submit that certificate in your homework folder by class time next week, just like you would normally do. Also, the Wednesday lab hours at the Reston Center, if the weather clears up and the campus in Nova is running, the Reston Center will be open and you can access the lab if you need it, but I will not be there to assist you. This shouldn't be a problem because you really don't have any lab assignments this week aside from completing the ESRI online learning module, the OLM. And this week, the one we're doing, OLM 3 on your syllabus, is finding geographic data in ArcGIS. And as always, if you have any questions about any of this stuff, please do not hesitate to send me an email. I'll try to respond to you in a fairly timely fashion and answer your questions. But basically, we've got a relatively short lecture, just some things for you to learn. There's no chapter assignments this week per se, so just do the lecture and then complete your online learning module 3, and after that enjoy your snow day. So we're going to lecture today from the ESRI Guide to GIS Analysis Volume 1, Geographic Patterns and Relationships. This is the text by Andy Mitchell. We're going to cover chapters 1 through 3, essentially the first about 69 pages of the book. And so chapter 1 is an introduction to GIS analysis. We're going to talk a little bit about what GIS is, understanding geographic features, and understanding geographic attributes and what that means. So what is GIS? Geographic Information Systems. It's a system designed to capture, store, manipulate, analyze, manage, and present all types of spatial or geographical data. And this is a pretty comprehensive and generic definition of GIS, and this one comes from Wikipedia. What we're going to do is look at what that means and what makes that, what is the makeup of that. And so the first thing is that GIS is basically 5 components. There's the software, like ArcGIS that we're using in class. There's the data. An example would be perhaps something like a digital elevation model. There's the people. That would be the analysts, or in our case, the students. The methods, the various techniques, whether it's something like an interpolation or a local indicator of spatial autocorrelation, a LISA, or other different methods. And there's the hardware, some PC or some other device that executes these methods on this data as prescribed by the operator or the analyst using the specific software that you're doing your analysis on. So what is GIS analysis? Well, technology approximately 45 years old. It has become really widespread in the last 25 years. If you go back further than that, it was pretty sketchy in terms of what was out there and what was available, but it has really exploded in the last 2.5 decades. The most common activities in GIS are pretty simple things: mapping where things are, mapping the least and the most, mapping the density, finding what's inside a particular geographic area, or finding what's near a particular area, and mapping change. These various activities are the most basic types of analysis that you do with a GIS. So what is GIS analysis? Well, it's really a process, and it begins with framing your question. And framing your question is looking at the problem that you have at hand, or the question that you're trying to answer, and positioning it or framing it such that you can leverage spatial data in the software to answer a question that otherwise would be difficult to answer without GIS. In order to do this, you have to understand your data. You have to know where the data came from, how it was collected, why it was collected, what are the limitations of the data, what is the data's quality relative to your intended use, all these sort of things. And then you have to choose some sort of method for how you're going to utilize that data. And then any processing that has to occur relative to that data is important. And ultimately this leads to looking at the results and determining in fact what the answer is. So one example of framing your question would be, where is gun violence occurring? Now, in order to do this, you have to understand your data, and that means differentiating between things like accidents and suicides and other shootings. Because if we're specifically looking at gun violence, do we consider accidental shootings and suicides the same as we would other shootings? And you have to know the data and know the intent of the question in order to do this. And one way that you might do this would be choosing a method by something simple like density mapping, where you simply map the frequency of these events occurring over a spatial area. And ultimately you're going to process that and make some sort of a map. And from that you're going to gain some kind of knowledge, because you're going to be able to see the locations where you have higher levels of this particular phenomenon occurring. So that is what we do with GIS. It's changing data into understanding. So, understanding geographic features. What are some of the most common GIS activities? Well, these are the ones that we've already went over, but we just covered mapping where things are. Now let's look at mapping the most and the least. Alright, types of features. Features tend to occur in one of two formats. Discrete features, where it's clearly defined, as in this is the swimming pool, or this is not the swimming pool. This is a particular county, this is not a particular county. This is on one side of a road or the other, sort of things. And then there's continuous phenomena like elevation, temperature. Oddly enough, one that we should be really familiar with today, precipitation, and how much snow occurred at different places. These are all different types of examples of types of features in GIS. And so then the next thing, of course, is how we represent that. And we have two general formats, vector and raster. Vector being points, lines, and polygons, and raster being this grid network of cells. And then, of course, we have to use our projections and our coordinate systems to take this 3D roundish Earth and convert that into this flat two-dimensional map. And I really think you guys have made pretty remarkable strides relative to Chapter 3 in our other text as far as projection and coordinate systems. I'm really pleased with the progress you young folks have made. I think by the time you complete the degree program here at Nova, you will probably understand this better than any group of students that I've had so far. So, what are geographic attributes? How do we try to understand these? What do they mean? Attributes are information about some place or something with a defined spatial location. This is sort of my definition. When we talk about spatial attributes, it's really I have this knowledge, this fact, this measurement, this description of something that has a defined spatial location. Now, there are common types of attribute data that would be things like categories and ranks and counts and ratios, and there are tabular data formats, and we use them because they're helpful. They allow for searching and selecting and calculating and summarizing of a lot of things and data and facts and information. And so we use this different stuff basically so that we can take the knowledge or the information that we have and convert it into new knowledge. So chapter 2 in the Andy Mitchell text talks about mapping where things are. So we're going to talk a little more specifically about mapping where things are, deciding what to map, preparing your data, making your map, and then analyzing patterns. So why map where things are? Well, the obvious reason is to see where things are. I mean, that's sort of self-explanatory, but that's really kind of important. It's one thing to know where things are, but it's another thing to see them in the context of how they relate to other or similar things. We also need to understand what is at a specific location would be a reason. Maybe we know or we have an area that we're interested in, and it's not so much that we looking, for example, where all the 7-Elevens or where all the Targets are. Maybe we want to know what stores are near a particular area, so we want to map the location and see what's there as opposed to mapping where something is. And all this comes back to allow us to make decisions. Once we have this knowledge, our decisions are informed and grounded in spatial reality. In other words, we make decisions about where we place buildings or where we choose to open up a coffee shop. Where other coffee shops are at could be an important tool in this. Where residential foot traffic is common might be another thing to consider. And the next evolution, if you will, of this understanding of where things are is the ability to spot patterns in relationships. And I've mentioned in class multiple times that the human mind and human eye are some of the greatest pattern spotting softwares ever developed. And through years of evolution, we've reached a point where we actually identify patterns that really aren't there. In other words, we tend to see patterns that statistically are not relevant because pattern recognition is so important in terms of finding where the safest path is, or identifying locations of danger, or looking for the least difficult path and things like this. We always just have been we've evolved to look for these things, because the people who lack the mental capacity to spatially do these sorts of things were at a competitive disadvantage in the early development of human existence, and simply put, we're probably not the ones that made it through the hard times. So once we do these things and we start looking for patterns, and it helps us make decisions, and we can understand what's at specific locations, and we can see where specific things are located, it helps us understand the spatial configuration of what's going on in an area. It helps us to understand the spatial configuration of the phenomena that we're looking at, or of the properties of an area that might relate to a phenomena of interest. So, that said, how do we decide what to map? Well, to ID patterns, you need to know what you want to map. And the way you do this is you look at what information do you need. What do you need? What's your end product from your map? And once you know what that is, then you can start sort of working backwards. So I know that I need to identify this. This is related to this specific data. And you have to figure out a source and a place where you can get that data from. And that's how this works. And so the third step, how will you use the map or information? So now that you know what you need, you figured out what information you need to get to that, you need to consider how you're going to use that information, how are you going to map it, how are you going to display it. And the other part of that is, who is the map for? Once you've sort of narrowed down all these things, and you've determined that you're trying to look for patterns in phenomena X, and you figured out what data you need, data what, in order to figure this out. Then you can decide what types of things you need to do in the map to do this, and then you have to at the end stage, if you will, of the initial process, you got to figure out who's going to use this map or this explanation, and make sure that the product that you're producing can infer the information that you're trying to infer to that particular person. So how do you prepare your data? Well, number one is you have to have spatial information. All the data in the world is wonderful, but the majority of it does not have a spatial component, or at least a readily available spatial component, and that can make it pretty much useless for mapping things. And so if we have this spatial information, it allows us to move forward and do a lot of cool and interesting things. But the first step in that process is the geographic coordinates. You have to assign some spatial location to the data points, and then you have to assign or categorize the data so that you can make sense out of it. And then you need to be able to assess the data quality. Remember, the definition for data quality is the ability of a data to meet the specific requirements of a given analysis. In other words, it's not a hard and dry, this is good data, this is bad data. Good data is data that is of adequate quality for its intended use. So next step is making your map. So you have to decide what you want to display. What's the thing? It's kind of an old lesson, a life lesson, if you will. They said, hold up your hand and look at your 5 fingers, and these represent the 5 most important things in your life. And if you take 3 fingers and your thumb and pull and ball them into a fist and just leave up that one finger is that thing that's left, the thing that's most important. And obviously, if you take care of that thing, what happens with the others is far, far less important. And so that's kind of what we deal with the map. There's lots of ways you can display things. There's lots of information that is potentially important that you might like to share. But if you lose sight of that single thing, the reason that you started the analysis, the reason that you collected the data, the reason that you answered the question, that's what's important. And so the answer is what you have to think of. The answer to your problem, the answer to your solution, the answer to your question. That is what you must display first. That is the point that has to be made clear. That is the point that has to come through to everyone that uses your map. And so there's different ways of doing that. One, you can map single features. Now, you can, and often do, include multiple types of data. And so it's not just that one thing. Maybe those other 4 things, if you will, out of that top 5 you can include. But the important thing is, you need to make sure that whatever choices you make, it does not impinge upon that most important element's ability to be relayed to your map users. And so you can map a lot of things. You can map subsets, you can map categories and types and scales and groupings and colors and symbols, and you can use all kinds of clever symbology like we've went over in class already to do a lot of really cool stuff. But if at the end of the day it doesn't help you answer your question or make your point, it's all been for naught. So we talked a little bit about pattern analysis, so let's talk about that some more. Mapping data can disclose patterns that are otherwise unseen. Things that we might suspect, or maybe in some cases things that we didn't suspect, are obvious when we analyze the data and we look for geographic patterns. And when we talk about geographic patterns, what we're really talking about is the occurrences of a particular phenomena, or those spatial locations where things are occurring, or the relative high or lowness of a value across the surface based on sample points. Are the high or low values clustered? That's the big thing we look for, clusters. Clusters would be clumps of similar or like values. Now this could be all the high values are in one part of a field, for example, and all the low values are at the other end of the field. Obviously then you would know that there's something going on spatially, more so in one area than there are in another. Data can also be uniform. In other words, we have sort of a random dispersion of high and low, and they're spread out, in somewhat of a, non-clustered pattern. It's sort of, you think of uniform as the opposite of clustered. Then there's dispersed. And dispersed is kind of unique because it can often be mistaken for uniform. Dispersed is when the data is literally positioned so that it is as far away from each other as possible. It's like when you hold magnets up to one another. If you hold a negative side of the magnet up to a negative side of another magnet, they repel each other. Think of your data points or your values as being, being magnets of the same sign, and so that they try to space themselves as far apart from one another as possible. That would be what dispersed would be like. Then there's various advanced techniques that we can use that help us identify the types and kinds of clusters that may or may not exist in our data. Chapter 3 is about mapping the most and the least, and so this is sort of the next logical extension from looking at what we actually know and where it's at to mapping amounts and levels of things. So why do we map the most and the least? What do you need to map? How do you understand these quantities and create classes in making your map and looking for pattern? Alright, so why map the least and the most? Well, the obvious one is to find places that meet a criteria. It can also help you add additional information to things. So what do you need to map? Well, you can map features of similar values. You can map discrete features. You can map continuous phenomena. You can summarize data. The big thing is you have to keep intent in mind. And what I mean when I say that is there's always multiple ways that you can map things. But what you have to figure out is what's the best way to map the data that you have to make the point you're trying to make. And for example, if you're mapping the least and the most in terms of finding a criteria, you need to keep that in mind, that the intent is to show, for example, the location with the least competition, or maybe it's the location with the most customers. And so from this, we can add additional information. We could take, for example, if we're looking for places with the most customers, we could also then categorize those customers relative to age, because maybe not all aged customers respond in the same way to a particular product. In other words, say we're looking for a location to place two stores, one being a coffee shop and one being a tattoo parlor, for example. It might be that the coffee shop crowd would be a slightly older crowd than maybe the tattoo parlor crowd, and so that while we might still be looking for the places where we have the most customer potential in terms of population, we could break that down demographically and look at the age groups and further identify maybe there's a particular region in the populated area that's best for the coffee shop, and maybe there's a different area that's better for example, the tattoo parlor. Other reasons that we do this is to understand quantities, and when we talk about that, we're really talking about just sheer numbers, the counts or the amounts. How many of these things occurred here, how much precipitation was there, and sometimes it's ratio. Sometimes we're looking at people per square mile, or maybe we're looking at the ratio of people under the age of 7 versus people over the age of 80, so we can determine what locations, depending on how that ratio goes, might identify areas where you need to target new preschools versus new elderly activity centers or something like that. And we can also do ranks. Ranks are important because maybe it's not a hard and fast scenario where we're looking for a definitive number. We simply want to know if we have the resources to do X among these 5 options, which is the best one. And so we can apply some criteria and then say, okay, this is the location that needs this the most. It doesn't necessarily mean that it needs it, it just means that it needs it maybe more than the other locations. And we do a lot of this stuff by creating classes. And the problem with this is classes are a trade-off. It's a trade-off between accuracy and representation. Anytime you classify your data, you're losing some information because you're taking the nuanced and detailed data that you have and clumping it together into blocks or groups. And so what we do lose in terms of accuracy, we may make up for in terms of our representation because it allows us to more clearly identify patterns that maybe wouldn't be as easy to see in some other scenarios. There's also the issue of individual values versus classes. Individual values in some instances are really important. In some cases, the classes are fine. But you have to be careful because you can make classes that might mask a particular phenomena, and so individual values might be more appropriate. So the validity of the ranges of classes is important. We've talked about this in terms of the different methods and how you select them. So you have manual and you have standardized classifications, and the 4 big ones that we talk about are natural breaks, quantiles, equal interval, and standard deviation. Of course, standard deviation is based off the distribution of the data. Equal interval is just a set interval. Quantiles is it's a different variation off of the distribution of the data, and the natural breaks, of course, is the technique that seeks to have the smallest possible average standard deviation across all groups. So how do you choose? Well, you look at things like your data distribution. Is it evenly distributed? Is it unevenly distributed? Do you want to emphasize differences between features or the relative differences between features? Are you trying to identify outliers, or are you including outliers? Are you removing outliers? How many classes are you going to have? These are all legitimate and not easily answered questions. So it sort of falls back to making your map. You have to think about your audience. You have to think about things like graduated symbols, graduated colors, charts, and contours. What type of map are you going to make? How many variables are you going to have? Are you going to create 3D perspective views? Are you going to exaggerate things to show the relief being more pronounced? Are you going to use lighting techniques to identify terrain? There's lots of things you have to consider when you're making your map, and all of it plays in again to how can I tell the story that I want to tell? How can I make my data understandable to my intended audience? So, looking for patterns. Talk a little more about this. Looking for patterns is important. It helps us establish relationships between different data types. It helps us understand the phenomena that we're analyzing. The problem is it can be influenced by the map, and so you can make maps either intentionally or accidentally that make patterns appear to exist when they don't exist. You can also create maps that influence it such that patterns that do exist are not as apparent. And the bigger issue is not only are these influenced by the map, but they can be influenced by the map maker. And so you have to work to really be open-minded and unbiased in the decisions that you make. Try to be true to the analysis, true to your employer, and more importantly, true to the facts, and not look for ways to kind of work around those things. So you have to think spatially, because that's what it all comes down to, is the software, the hardware, the techniques, the data, the really clever questions. All these things are wonderful and great. But they're really hard to wrap your head around sometimes, and that's where spatial thinking comes into play. And spatial thinking is the culmination of all the skills that we've covered so far. I like to say it's the most important skill to develop and the most difficult skill to master. It's your ability to look at a problem and think about it in the context of real space, and think of how it could be related to other phenomena, other data, and to leverage all that into this analytical construct that you've come up with for I have this question that has a spatial component, and I know that I can get this data and this data and this data that all have a spatial component, and I can construct a geographic information system in a way that I can leverage these desperately different sources of spatial data to come up with a spatial answer to my problem, to answer a problem that otherwise outside of a GIS would be so difficult to do. And so this is not something that we're going to talk about for a day and you guys are all going to get. This is not something that you can say I'm having trouble with and stop by my office and I'll give you a 5-minute pep talk and it'll all be wonderful. This is a skill you have to work at. Some people are of the opinion that you can either think like this or you cannot. I don't know if that's the case or not, but I do know this. We can all get better at it if we work at it. And so the way we're going to do that is by proceeding with things like our class projects, so that we begin to work through this process of how we solve problems spatially. I'll learn how to format spatial reports and things like that, so that we can share this information with others, not just in the context of maps, but in a broader sense. And as you move into your next GIS class, instead of being assigned a problem, you'll come up with a problem on your own, something that's unique, something that matters to you perhaps, and you'll begin to apply these same sort of concepts, but at a deeper level of understanding and a deeper level of commitment in terms of what you're going to do to solve those problems. And ultimately you will get better and better and better. And will you ever reach that point to where you've truly mastered this concept of spatial thinking? I don't know, but I promise you that if you work at it and you're committed to it, you will get better at it. And as you get better at it, you'll become much more effective using GIS, and you will make yourself potentially a much better GIS professional. So that's all we have, I think, for this lecture. I know it's been relatively short and it is a very general concept, but I want to make sure that you guys have read the first 70 pages in the Mitchell text. If you haven't, utilize this time this week, since you don't have any lab homework to do other than your online learning module, to go back and read the chapter. There is so much more information on each of these topics that I've discussed so briefly, and it is a really good desk reference text, and so it will be worth your time, particularly now that even if you've already read it, but now that you've listened to my sort of take on these key components, to go back and read through it again and look at all the wonderful illustrations and examples that they have in the text. And I think it will really start to get your head wrapped around this concept of spatial thinking and prepare you for true spatial analysis. So stay in out of the cold, don't get frostbite, get your homework done, and I'll see you next week.